All right, we're going to take a little side quest here, and we're going to look at estimation, graphs, and mathematical models. Now, estimation is one of those things that there are more than one right way to do it, which makes some of the problems in the book or problems in the Pearson homework sometimes harder to get exactly what they're looking for. Generally, when we estimate at this level, what we'll want to do is we'll want to get it so that we're only dealing with one number. What we want to do is simplify our multiplications by estimating. So I'll try to show some examples, but please, if you have any problems with the homework, ask questions on it. In most cases, it's because people are so comfortable with a calculator check that they don't estimate freely. Generally, for most of these estimation problems, we should be trying to do them in our head. And so, what we're going to do in this chapter is we're going to use estimation techniques to arrive at an approximate answer to a problem. We're going to apply estimation techniques for information that comes from graphs. And then we're going to look at making mathematical models. And mathematical models, really what we're doing in all of this is we're using estimation to do some inductive reasoning off of the graphs, but we're going to apply induction to the numbers that come out of it so we get a formula. Let's say formula might not be the right word, so I'll go to the more generic and go a relation, how the numbers relate to each other. I think some of the things that we will see is we are actually looking for how different collections of objects relate to each other. And in a lot of our early cases, we'll start that with numbers. So when we look at an estimation or ways of finding approximate answers, we will look at rounding. And rounding is a process that there are actually many ways to round depending on the context. We're going to use the up or down method of rounding. Graphs also can visually give us a feel for a quantity without the exact number, so we can approximate the numbers on the graphs. And then in mathematical models are ways of getting an answer, or at least an approximate answer, from previous inductions. So rounding whole numbers, I'm going to read the rules here, and then we're going to look at one. We pick a place value in our numbers that we're going to round to. We're going to round to the nearest tenth. We're going to round to the nearest tens place. We're going to round to the nearest hundreds place. And so we pick that place, and that's the place that is going to be our best measurement. Anything to the right of it, or any smaller value, is going to be dropped and rounded. And the rounding rule we're going to use is if the thing to the right of the number we're estimating for is 5 or greater, then we're going to push the number we're looking at up by 1. If the thing to the right of the number we're looking at is less than 5, then we won't change it, but we'll fill in zeros. So we'll take these rules and we'll make these rules work for us here. Let me get back to the blackboard. Let me scroll down here. So let's say I have 5,384, and I'll put the comma in. So one of the things about these numbers that came from India, Hindi numbers, is they worked on giving each place a value. Again, these did not come over into Western culture until 1202. Let's see, how would this have been written in, let's see, MD, let's see. These would have been written in Roman numerals. I'm trying to remember what 5,000 is. because 1,000 is M. Whoops. Did I lose my place here? Trying to, well, it looks like I cleared my screen off here. Alright, let me redo my number. There we go. Got my number back. Yes. Sorry about that. There we go. So 5,384. I'll give an example of Roman numerals. Let's do 384. In Roman numerals, that would be CCC. L X X X IV. And so each of these had a value, and you had to count them up, but place didn't hold any value here. In Hindi numbers, or Indian numbers, which came into Western culture via the Persian Empire, each place had a value. So this is telling me about the quantities. This is saying I'm going to expand this out. It's going to look really ugly, but it will tell us what's happening here. This is 5 times 1,000 for this first place, plus 3 times 100 for the next place, plus 8 times 10, plus 4 times 1. And so each one of these values, as we move to the left, talks about more things. So this 5 is talking about 5,000s. This 3 is talking about 300s. And we can write that as a multiplication. In fact, it works out a little more cleverly that if I think of 1,000 as 10 to the power of 3, then in my place values, are all powers of 10. And anything to the 0th power is 1. And so we say our number system is a base 10 system. And this also continues to the right of the decimal point, where the place value here would be 1/10, the next one would be 100th, and so on. So this system was invented, again, if you watch the video on the history of the number 1, the Indian culture invented these numbers to deal with the theological problems they were trying to calculate. Right? How many times does a god's eyes blink as it makes a stride? How many strides can a god walk within a moment? And they were dealing with very, very large numbers. So they invented a number system that could go very large. It really is the basis of kind of how our modern technological world works, was us inheriting this number system. But it did take hundreds upon hundreds of years for this idea to pass through cultures. Now let's go back to 5,384. And I'm going to talk about estimating. So the first thing I'm going to do is I'm going to estimate this to the nearest hundreds place. So I'm going to mark the hundreds place. And I'm going to immediately look to the right of it. And I'm going to ask myself, is 8 bigger than 5? And it is. So my estimate is going to be 5. Since 8 is bigger than 5, this is going to go up to 4. And then I replace these two places with 0. And so 5,384 is approximately 5,400, or to the nearest hundreds place. But maybe my estimate needs to be different. Maybe 5,384 needs to be to the nearest tens place. So I look to the right and I go, hey, I've got 4. Is 4 bigger than 5? Well, it isn't. So I don't change the 8. And so 5,384 is approximately 5,380. It depends on what we want to round it to. Maybe I want to round it to the thousands place. And so I go 5,384. That's the place I'm going to round to. So I look to the right. Is that bigger than 5? It isn't, so I don't change this number. And I change these all to 0. So 5,384 is approximately 5,000. It really depends on what we're estimating to. What we're estimating to tells us how accurate that approximation can be. So that's how these rules work their way out on numbers. Here is another example. We want to round to the nearest million because world populations are, nearest 100 millions. Now, each comma is a different named branch. So the first comma gives me thousands. So this is 169,000. The next comma gives me millions, 843 million. The next comma gives me billions, and so on. Everything is in groupings of 3. And so the comma works its way across, and we get different named portions of the number. So the nearest 100 millions is going to be this 8, because that sits in the 100 million spot. So we look to the right of it, and we go, is this bigger than 5? And it isn't. So we replace everything to the right of 8 with zeros. And so the world population is approximately 7,800,000,000 because we rounded to the nearest millionth. Or I'm sorry, to the nearest 100 millionth. The next question says round to the nearest million. And so again, I'm going to look at the 3, which is in my millions place, not my 100 millions place, but my millions place. I'm going to look to the right of it and go, is this number bigger than 5? Well, it isn't, so I fill the rest in with zeros. And so the world population rounded to the nearest million is 7,843,000,000. And we can do the same to the nearest 1,000. 100,000. So I look at the 100,000 place, and I look to the number to the right of it. Is it bigger than 5? Well, it is. So I'm going to increase this one up to 2, and I'm going to fill everything to the right of it with 0. We can do the same thing with decimals. Because larger values go to the left and smaller values get to the right, it's still the same process. We look at the number in the place. So I want to round pi to the nearest 100th. So I go to the 100th place. I look to the right of it and I ask myself, is it bigger than 5? Well, 1 is not bigger than 5. So I'm going to keep the 3.14 and I replace all of these with 0. But because I replaced all of these with 0, they don't give me any more information, so we can drop them. And that's why pi, it can be rounded to 3.14. Now, estimating by rounding is used often. I do this all the time when I'm in the grocery store, is I will round. I will look at the price of things I have, I'll round them, and I usually round to the nearest dollar, which is what this example is doing. It takes a list of different items and rounds them to the nearest dollar. So bread at $2.59 gets rounded up to $3. Detergent at 517 gets rounded down to 5. A sandwich at 365 gets rounded up to 4. An apple at 47 gets rounded down to 0. And coffee at 879 gets rounded up to 9. Well, 3, 5, 4, 9. Well, 3 and 5 is 8. 8 and 4 is 12. And 9 and 12 is 21. This is a way I keep track of stuff as I'm buying it. Now, if we go back and add all of the items, we get $20.67. So estimation usually is done to do quick ways of doing mathematics. A lot of times what we try to do is make the number easy enough that it falls within our addition or multiplication tables that we know, so that we can get an idea if an amount is right. In fact, this question is saying, hey, someone said it was 2467. We do a quick estimation, we get 21. That's off by $3, which seems high. And so going back and re-adding all these up, it was 2067. So there was something wrong with the original bill. Another tool used for communicating quantity is graphs. And circle graphs are a great utility because what they do is they visually give you an idea of how much stuff is there. So in this circle graph, visually, we look at the whole. And then in this larger chunk of the whole is not quite half of it. This next larger chunk is a little more than a quarter of it. And by kind of being able to divide it in half, visually we get an idea of percentages. Now, if I was presenting data, I would put the percentages in here. But we don't need to compare the percentages because the graph visually shows us one chunk is larger than another chunk. And we get an idea of how much of the whole each of these things is occupying. And so circle graphs are a great way of representing information without needing to know the exact amounts upon it, because the area covered in the graph is related to the actual percentage of something inside of a whole. So in this case, Americans' definition of old age, they were given survey questions on what it was, and this is the percentage of what people answered. So if we look at the previous slide, we could answer an approximation here. So according to the U.S. Census Bureau, in 2020, there were 249,019,818 Americans 25 years and older. Assuming the circle graph on the previous slide is representative of this age group, the people that were asked, use the appropriate information displayed by the graph to determine a calculation that shows the number of Americans 25 years and older who defined old age by a decline in physical ability. Use rounding to find a reasonable estimate of this calculation. So, a decline in physical ability is 41%. So, what I can do is I can take 41% on a calculator and I can multiply it by the 249,019,818 people. And we plug that into the calculator and we get that's rounding. Let me get my calculator estimate here. Let me pull up the calculator. And so 249, and it is not showing up on the screen, but I've already started to type it in. So get your calculator out and try the same. Times, and I'm going to use 0.41 for percentage. And when I multiply that together, I get 102,098,125.38. But we'll leave it at that. Let's see. Can I get that displayed here? Can you? Nope. Ah, wait, there. Maybe you can see it. There's the calculation. Sorry, when I have to display the whole screen because the software I use to switch between screens, you'll get that like Doctor Who-like effect on it. And so if I multiply 249,019,818 by 0.41, which is how we'll talk about a percent, we get 102,098,125.38. But an estimate might be a better way of dealing with this. So let's look at how we might be able to estimate it. So if we use 0.4 instead of 41, and we use 250,000 instead of 249, or I'm sorry, 250 million instead of 249,019,818, it makes these numbers easier to deal with. In fact, we can look at 4 times 25 is 100. And then we have to worry about moving the decimal place. So 4 times 25 gives me 100 million, approximately 100 million Americans. And again, if we compare that to the number I had before, I got 102,098,125.38. For this number, 100 million is not a bad estimate. And in general, what we want to do is we want to minimize the calculation. We want to get our calculation to be numbers that are actually going to affect the multiplication within the times tables we know. So 4 times 25 is the easiest approximation here. The only thing we have to do is keep track of how many zeros we're dealing with. Okay, so 4 times 25 is 100. We put 1, 2, 3, 4, 5, 6, 7 zeros behind it. That's going to give us a billion. We move the decimal place by 1. We get 100 million. The last thing we're going to look at in this section are bar graphs, which, like the circle graphs, use height to show value. They usually do this so that we can look at things either moving through some measurement. So we can use these also to make predictions because we can continue visually moving in the direction of the graph. And the directions of the graph move left to right like the predominant reading direction. So here is a graph that charts 2 pieces of information: the life expectancy in the United States by the year of birth from male and female. So the life expectancy of someone born in 1950 is 65.6 male, 71.1 female. If we follow the male peaks, it's rising slowly. And this is happening every 10 years. If we follow the female graphs, it's rising also. So what we can do is we can use this graph to talk about what that rise is. And what we can do is we can take the number of years from one point to another. So my beginning of the graph is in 1950. My end of the graph is in 2020. So if I take 1950 and 2020, So if I take 1950 and 2020 and subtract them, that's 70 years have passed. So this graph covers a change of 70 years. Now, if I also look at the change in, and let's look at the male population in the life expectancy in years. So at the end, it's at 77.1, and at the beginning, it's at 65.6. So we take the 75. Where's the 77? Now I have to think. 77.1, sorry. 77.1 minus 65.6. So in the course of the graph, the life expectancy years has changed. Well, 77.1 minus 65.6. This is why I have a calculator. Is 11.5 years. And so what we have is this is changing. It changes 11.5 years expected every 70 years. And the way of writing it as a fraction, notice we're saying the life expectancy of a male changes 11.5 years per 70 years. Per is the sign for division in language. And so we're talking about the change in expectancy divided by the number of years. This is a good way of modeling change. The change in the outcome divided by the change or duration of the events. This has the name rate of change, and when we go to graph, we'll also call it a slope. A lot of times the notation mathematicians will use for this is they'll use a Greek delta, which looks like this, to represent the word change. And when we have a graph like this, we have birth year and life expectancy. Birth year on the horizontal axis and life expectancy on the vertical axis. Then what we can do is we can use that as a way of talking about the change overall. So we could estimate that overall change. Let me see here. I'm trying to... I have the slide up and I need to... And I think you guys are seeing the blackboard. Let's go to the slide here. There we go. So if we look at the number of years expectancy or the outcome divided by the number of years that have passed, this is approximately 0.16. This is something we can run to the calculator to do. So 77.1 minus 65.6 divided by the, in parentheses, 2020 minus 1950. Let me check it out. 0.16428. 0.16 is going to be close enough for us. Well, if I want to figure out the life expectancy in 2030, then I've got to go 70 years out. And so I take 70 more years times the change per year, which is 0.16, and I add it to the starting value, 60.56. Generally, and let's see here, I want to switch to the blackboard. We say that we're going to take the starting value plus the rate of change times the number of years or whatever's changing. Well, right now we're going to talk about time changes, but that horizontal axis can have different changes on it. These words hide two mathematical operations. So a lot of times these will get abbreviations. So the rate of change is M or R, depending on what you're doing. And the years, since it was on that horizontal axis, we tend to call it X. So we'll say times X. And then in that starting value, for historical reasons, is usually called B. And what we're going to find is we're going to get a lot of examples where we'll do something by word. And we'll eventually find a way of talking about it where those words get broken down to symbols. The best way I say it, since I have degrees in physics and astronomy and do a lot of mathematics, I will blame mathematicians, because I am not technically one fully, is mathematicians are lazy. And so in chapter 6, we'll write this as Y, where Y represents the output of whatever's happening. In the example we're looking at now, it's the life expectancy, is equal to the rate of change, M, times X, plus the starting value called B. And this is also called an equation of a line. We will work towards this over the next couple modules. But what we're doing right now is we're taking these words and looking at the values that were in them. And so there's my starting value, because there's my starting value, 65.16. We calculated the rate of change over the course of this whole graph. And then we asked ourselves, if this is our starting year, how many years does it take me to get to 2030? And so 10, 20, 30, 40, 50, 60, 70 gets us across, right? We move across, it's 70 more years to get to 2030. And no, it isn't. This is a typo, I think. Oh, now I'm running to the calculator. Give me 1 second. The new slides, do they have a typo in it? Let's see. 80 times 0.16. Yeah, this number here should be 80 years. Because notice when I was counting out the years going through. So the textbook made a mistake, and I didn't even see it on the slide. It's a new textbook for me. I used the previous edition before. My apologies. But it is 80 years out. And so this should be 80. And notice how I was counting. From 50 to 2030 is 10, 20, 30, 40, 60, 50, 60, 70, 80. And so we'll put 80 years here. Let's see, can I change it here? Try to make sure this slide is different than the ones that are accessible up on the web page. I'll double check to make sure that is correct there. But that we have used words now to describe what's going in here. We will slowly work our way to using nothing but symbols. And the other thing we can do with graphs is instead of looking at the top of the bars, we can connect them together with lines so that we can get a visual clue of how the change is going. This could have been a bar graph, with these being the peaks as different bars. But by playing join the dots with the top of the bars, we get some information. We notice that between these two dots, we can kind of pretend we're mountain climbing or hiking on it. And we can see where things are changing differently. So also why the rate of change is called a slope, because it looks, when we graph it, as the steepness of how it's changing. And so we can use that then to describe the things. In fact, a lot of times with graphs, what we want to do is we want to borrow our ability to navigate our local geometry and the words with it to describe how the numbers are changing that we're looking at. And so here it's falling slowly. Here it falls more slowly. And then it rises rather quickly and drops very quickly here. Well, having grown up in the 90s, right, smoking was found to be caused cancer. And so there was a decline in smoking. And then come the 90s, there was a very successful ad campaign with a cartoon camel, Joe Camel, and Camel Cash, or promotionals, and Marlboro Miles and promotionals that gave prizes away for cigarettes. Well, that led to more people smoking. Then it was slowly banned in public places, and that led to more decline in it. So we can kind of correlate what's happening here if we knew some historical events in it. But those changes we can look at in how this is shaped. And so we can use this line graph to also approximate, because we can look at a point and we can ask ourselves, well, it's somewhere between 16 and 20. So we'll say that's 18%. And so this was in 2010. About 18% of college students were smoking. We want to look at what year did it decrease at the greatest rate. So we look at how the place where it drops the greatest. And if we look here between 2010 and 2006, or not 2010, 1990, 2000, let's see, add 4, 2002 and 2006. That has the steepest fall. So in which 4-year period did the percentage of college students who smoked cigarettes decrease at the greatest rate? Well, we're going to look for the greatest fall on the graph. And that's what it does here. It looks at this greatest fall on the graph from 2002 to 2006. Because it's visually the thing that's dropping the most. In what year did 30% of college students smoke cigarettes? So we come back to the graph and we look for 30%, which is kind of the peak here, and that's 1998. So there's a lot of information that we can encode within graphs, and we use kind of our positional geometry to decode that information. I'm going to leave example 8 for reading in the text, as it is exactly the same as the example, well, not exactly, it is the same methodology as the example we looked at with male and female life expectancy, except there's only one piece of information here, not two embedded. So we can look at taking the value at the end minus the value at the beginning, the year at the end minus the year at the beginning, and get a rate of change from it. So I'll let you work through that last example in the slides and play with it, as there's a similar question in the homework.